Yeah, so all of you can hear me, right? Just an yes or no answer, please. You can hear me, right?
Yes, sir.
Okay,
Yes, sir.
cool. Okay, great. So a quick recap. I think yesterday was a holiday. Quick recap, and then we will go on to see the model and the electrical model today, and then probably we'll start building circuits, start building the electronics portion around it. So what we discussed yesterday, I mean rather in the last class, was the constitutive equations and their forms. So there are four forms of the equation, and what we discussed is how the forms, I mean different forms are evolved, right? Or how the different forms, I mean how you can make meaning out of the different forms. So on one side we wrote the output parameters, the mechanical domain of stress and strain, right? And in the electrical domain, charge and voltage. And the input parameters we wrote on the other side of the table, right? And of course, we showed, the letters that we are using to denote the parameters. So the input parameters, strain, stress, again in the mechanical domain, and the output parameters, the input parameters in the electrical domain of voltage and charge, right? And then we said that if we are moving from you're talking from in terms of strain, and then we are converting that into stress, and similarly electrical field E, we are converting, the transducer is converting this electrical information from electric field E, it is converting it to the charge. And this conversion, we said, let's say we denote it by the conversion coefficient E, right? And then we said, okay, this is how the stress charge form is going to look like. And the name is derived from these two equations, sensor and actuator equation, right? So the first one is essentially the actuator, right? Because the output is a mechanical quantity, and the second one is actually the sensor, because the output is an electrical quantity, right? So, and the reason we call it stress charge, because the mechanical, when we are talking of the actuator, the output is stress, and when we are talking of the sensor, the output is actually charge. So that's the reason we call this stress charge, right? And we explained everything in this equation except why this transpose is coming. Today we are going to discuss that, why this transpose is coming, right? Rest, I think we have pretty much covered, how these expressions, or why these subscripts make sense, or how these expressions kind of come into being in the first place, right? So then, so this was the other two forms, strain charge and stress voltage. And then we have strain voltage. So these are the four constitutive equations. And then we also said that there must be a relation between these coefficients E, D, G, and Q, right? And there are 6 different transforms that will be there, right? Meaning we can move from E to D, or D to G, or G to Q, or E to G, or Q to D, right? Or vice versa, right? So total 6 kind of transforms are there, right? And we'll do an assignment also on that. And then a quick recap of the key points. Again, this is actually the sensor equation, right? In the electrical domain, only the electrical portion of it, right? P is the polarization which is happening because of the force that we, let's say, or the external field that we apply, right? And for piezoelectric, in the context of piezoelectric, P is equal to D times sigma, right? So that also we kind of discussed. And then we said that, okay, how do we represent piezoelectric behavior, right? In mathematical term, how do we represent it? So what I'm saying here, it's actually a tensor of 3 cross 3 cross 3 order, right? 3 by 3 by 3 order. And why it is like that? Why are we saying that it's 3 cross 3 cross 3? We will look at it. So when we look at sigma, so what is sigma? Sigma is force divided by area, right? Or you can say this is pressure. I mean, in other words, we can say this is pressure, right? So force itself is a vector, right? And when we are talking of this kind of a material that I have shown here, we can say that the force can be applied in three directions, x, y, and z, three directions. Similarly, area is also a vector, right? And the normal, I mean, if we are talking of this surface, right? So the direction normal to this surface will be the direction, I mean, will be the vector of this area, right? So essentially, so to describe, stress, we need to talk of two vectors, right? Each having three directions, right? This has three directions and area also has three directions, right? So sigma by itself is a tensor of order 3 cross 3 because we need two vectors and each vector can be defined or talked about in three different axes, right? Now, what will be polarization? What will be the rank of polarization if we have to define that in terms of a tensor? So polarization, what do we have to talk of polarization? When we say that, okay, this is the overall charge that is developed because of the force that we are applying on a certain surface. So what are the three things that are there? That we are saying that the charge is developed, charge or let's say electric field that is developed, right? Because of a force that is applied on a given surface, right? So we have here a vector, the surface itself is a vector, xyz, right? Force is a vector, again, in three dimensions, right? xyz. And similarly, charge or field that is developed, that also is developed in x, y, or z, right? So when we are actually talking of the polarization, I mean, we have to talk about the piezoelectric material and the behavior it exhibits, right? The polarization behavior, we need to understand total three components, right? There's an electric field associated with it, which has three axes, x, y, z. There is a force associated with it, again, which has three axes, and then there is an area associated with it, again, which has three axes. So it's essentially a tensor of 3 cross 3 cross 3 order, right? Any doubt on this? Any doubt on this? No doubts, right? Okay, so here what we are seeing, right, when we are talking of sigma, the stress, actually, this is actually, just the mechanical way of showing stress, and we have, I had promised you that I will not use sigma anywhere. It will be T everywhere. But because, it's a mechanical domain, just for the reference in this picture, I have used the term sigma or the symbol sigma. And what it means is, so when we are talking of a stress sigma, we have to denote two things, right? One is the force, and the second is the orientation of the surface. So sigma here I have written as sigma sigma subscript I j, which means I is the orientation of the surface and j is the direction of the force. So when we are talking of sigma xx, what it means is the force is applied in x direction, and it is applied on what? It is applied on an area which has its direction same as in the x direction. So when we say the area has a direction, what do we mean? The normal, meaning if we draw a perpendicular line from the surface, right, from the surface plane, so that direction is also in x direction. So that is sigma xx. Similarly, what is sigma xy? So sigma xy, as you can see, has been shown here like this, right? Meaning we are, the orientation of the force that we are applying is in y direction. Sigma xy, force that we are applying is in y direction. And on what area are we applying the force? We are applying the force on an area with a orientation in the direction of x. So that's why it is sigma xy. So if we see overall, how many such combinations can be there? Total there will be 9 combinations, right? 3 cross 3. So it can be represented in a 3 cross 3 matrix, right? Sigma xx, sigma xy, sigma xz, and likewise sigma yx, yy, yz. So this is clear, right? This is clear. Any doubt on this? I repeat, the way we have denoted it is the subscript I is the orientation of the surface. So first we talk about the denominator and then we go to the numerator. That's the way we have denoted it, right? So essentially, so for an isotropic material means a material which has, let's say, the mechanical properties are same in all directions. We can say sigma yx and sigma xy will be similar, will be same, equal. Similarly, sigma zx and sigma xz will be same. Similarly, in the same way, sigma zy will be equal to sigma yz, right? So the 3 by 3 matrix where we have 9 matrix elements, essentially there are only 6, right? There are only 6 matrix elements, unique elements, sigma xx, yy, zz or zz, whatever you call it, and then we have sigma xy equal to sigma yx, sigma zx equal to sigma xz, and sigma zy equal to sigma yz. And this is true because the material is an isotropic material, meaning it has mechanical properties which do not change with, basically there is no difference between the xy stress sigma yx and sigma xz. It's essentially the same. The material is going to behave in the same way, right? So there are overall 6 forces that we can, or stress we can associate with a cubic structure like this. Meaning, let's say this cubic structure is nothing but my piezoelectric material, and we can associate 6 different forces or stress directions or stress tensors associated with this kind of a material, right? So the simplified matrix form, when we write in the form of axial stress, actually here, even though I've mentioned the word shear stress, so shear in the mechanical guys will denote shear by tau or something like that. But here, just for ease of, or rather for simplicity, what I'm doing is, we have defined sigma like the way we did sigma ij, and then sigma was essentially a 3 cross 3 matrix, and because it was we are talking of an isotropic material, the 9 matrix elements, we said that we will reduce it to 6, right? And then when we are talking of polarization happens across like 2 different, meaning two opposite surfaces, right? And those surface directions can have, 3 different orientation. It can have orientation in x, y, or z, right? So the polarization, if I denote polarization as pi, where I can vary from I equal to 1 to 3. I mean, I can vary from, it can have 1 or 2 or 3, right? I can be across x-axis, meaning if you go back to the cubicle, the cube that we showed here, So we can talk of polarization across this surface, these two surfaces, or the polarization across this guy or this guy, or we can talk of polarization of this blue guy, of this blue surface, and of the opposite face, right? We can say, so basically there are three directions in which we can talk of polarization. So pi is nothing but a summation of these coefficients dik times sigma k. So dik is nothing but again the coefficient, the piezoelectric coefficient associated with what does I denote? I denotes the area vector and k denotes the force vector, right? So dik multiplied by sigma k, right? And sigma k, as we said, that it has essentially 9 elements, which we have simplified to 6 elements. So we have sigma 1, 2, 3, 4, 5, 6. So if we see, so P1, if we write like this, right, P1 is nothing but D11 multiplied by sigma 1. So what this means is sigma 1 is nothing but, let's say, sigma xx. The earlier matrix that we referred, so this guy that we referred, right, sigma xx is, let's say, sigma 1. So let's say this is sigma 1, this is sigma 2, this is sigma 3, and the rest we can say sigma 4, 5, 6. Any of these cross components we can say as 4, 5, 6, right? So polarization in the x direction is summation of all the stress that are applied in 6 different directions, and the stress is converted into polarization with the associated piezoelectric coefficient. So if we apply a force in the x direction, we can talk of the polarization that develops along the x-axis, and that conversion depends on this coefficient d11, right? Sorry. Similarly, sigma 2 is d12 sigma 2, and like this, right? The rest of the elements are like this. So essentially I can talk of polarization vector as P1, P2, P3. I can represent this in matrix form along with, so these are my material coefficients, right? Piezoelectric coefficients, right? And this is my force matrix or stress matrix, right? I shouldn't say force matrix, it's actually stress matrix, right? So any doubts on this? This is important because I promised you that I will explain why the transpose is coming in that equation, right? So up to this point, there is no problem, right? So I'm actually building towards that. So up to this point, there is no problem, right? Okay. So what we know? P is stress. We are familiar with this. How we are denoting the components. We are familiar with these quantities now. E is electrical field vector, D is the charge density or the displacement vector. So D and P, we have kind of used it almost interchangeably. Basically, it's essentially the charge that is moved or the charge that is formed on the opposite faces, right? And then D is the piezoelectric coefficient, right? So now if we have to write, so this is nothing but the direct effect, right? The direct effect, right? We are applying, the independent variable is stress and the dependent variable is the polarization that is developed, right? Because of the stress. So this is nothing but the direct effect, or we can say this is nothing but the sensor equation, right? So if we talk of the inverse effect, we have to talk of the inverse effect also, right? So there will be a strain associated with it, right? So we showed that the stress that is the stress components that are associated with it are 6, and that we explained, right? We saw why it is 6, because it's an isotropic material, and overall 9 matrix elements. We mapped it to overall 6, right? So stress components are 6. Similarly, the strain components also will be 6, right? Right? But the electrical field that we can apply can be only 3, right? So basically, this guy is a 6 cross 1 matrix, right? And this matrix is what? So this is 6 cross 3. And the electrical field, when we are talking of electrical field, this is what? 3 cross 1, right? So now you understand why, when we are moving from the electrical domain to the mechanical domain, or when we are talking about the inverse effect, why this D matrix is a transpose. This should be clear now, right? Why D is transpose. It's essentially got to do with the directions that we have for the electric field, which is 3, but the matrix that we have associated with stress or strain, that is actually a 6 cross 1 matrix, right? So whatever coefficient matrix we will have, that we can, by looking at the the matrix dimensions here and the matrix dimensions here, we can understand what will be the dimension of this matrix, right? The D coefficient matrix. So this is nothing but the transpose, this guy, this form is nothing but the transpose of this guy. And that is the reason in this equation, sorry, if we go back, so here we can see, right, we had used D transpose multiplied by E, right? So this is clear, right, why this transpose comes here. So whenever we are moving from electrical domain to mechanical domain, the coefficient associated with it has a transpose appearing. So here also you can see, right, this is electrical D, this is my Q coefficient, and this is stress. Similarly, the electrical component E associated with stress T, there is a transpose associated with it, right? So now is this understood? Why this transpose thing is coming into picture? So this was the only thing that we didn't discuss when we were talking about this table and how these different forms of the equation came, right? Clear now, right? Now we have discussed everything. Again, the name, the constitutive equation, stress charge means stress comes from this dependent variable, the output variable T, charge comes from D, right? Right? You can see here, charge, we call it charge, but when we are writing it, we write it in the form of electric displacement vector D, right? Similarly, this is strain charge. So we have strain and then we have charge. So this is stress voltage, stress and voltage. So instead of voltage, we write E. Similarly, strain voltage. And now we understand how these equations were formed, the domain equation and the transducer relation, right? This we discussed in details, right? How this equation is formed, why this is constant, C at constant electric field E, and what is the setup, that also we had discussed, right? Okay, so now that we have kind of covered, covered this, so this is kind of a recap, and I have shown this only for one form of the equation, strain charge. This pair of equation that I have shown here is strain charge representation in matrix form, right? So if any one of you go on to pursue higher studies with piezoelectric sensors, you will actually end up dealing with these kind of matrices and the values and how it kind of appears when you are actually fabricating the device. All of these will come into picture. But for now, we are going to leave this being an undergraduate course. We are going to not talk further into this, but this, I mean, it should be clear how these equations are formed, and the coefficients, when we are talking of the coefficients, the significance of the subscripts. Anything that you see missing here in any of these two equations? Anything you think I've done a mistake somewhere or something is missing? Something is missing, guys, in this? Come on, quickly. Anything missing?
Parts of equation.
Come again, please.
The parts of equation, like the d equal to small d t and epsilon e, but we have written the equation as polarization in terms of d and t matrices.
Right, no, matrix, that is fine. So what is missing if we go a couple of slides back, right? So, 1 second. So we talked of the strain charge form, right? So what is missing was that subscript epsilon t, right? Times, so this subscript is missing in that equation,
Yes, sir.
right?
Yes, sir.
Right. So this, there should be a, I will correct it in the, I'll correct it going ahead. So I've missed this out. But you have noticed this, right? And why this subscript comes, that also we have discussed in details. Do you guys, we are comfortable with this, right? Why the subscript is important? So the subscript is important. The subscript appears both when we are talking of, so epsilon is associated in electrical domain, right? Just like compliance, S is associated in mechanical domain, epsilon is associated with electrical domain. So whenever we are talking of the domain coefficients, either compliance or permittivity, we need to ensure that we are measuring, or we are kind of mentioning the condition under which that particular coefficient was measured. So when we say that this is compliance S, we have to say that okay, compliance S was measured in a given electrical condition when the electrical field or the voltage was constant. So E, it can be 0 or it can be something, right? But it will be constant. So we have to mention that. So this is just a recap. We have discussed this in details, right? That I don't want to go further back. So I think, okay, I will not go further back. It was there. The way we formed the equation, I think we had discussed it at that time, right? So now things are, I hope, at least the way these equations are formed, that is clear, right? So let's move on. So, so these are the four forms of the equation. I'm not going to talk about this again. This is just a summary. Strain charge, strain voltage, stress charge, stress voltage. And again, these are, so here I have not missed it out. I've written it correctly. So these are the, this is if when you are giving a revision, when you are going through the notes again, this slide will act as a quick recap of what coefficient means what, and the subscript and transpose, what that means should be clear. Okay, so this brings to the first assignment, and I will send you an email and your assignment will carry weightage for your overall evaluation. So the first assignment that I'm going to send a separate mail anyway, but if you want, you can take a note of this. The first assignment is you have to find a relation between the piezoelectric coefficients of the below constitutive equation. So stress charge. So basically, when we are talking of like stress charge and strain voltage, how are the coefficients related between these two forms? And similarly, strain charge and strain voltage. How are these two coefficients related? You will have to derive an expression for that. Any questions? So I will create a separate, I will upload this in Teams and you will have to submit your assignments in Teams. How much time do you think you guys will take? There will be weightage for this. 1 week? Is 1 week sufficient? Or do you think it will become too much for you guys? Come on, guys. Please speak up if 1 week is sufficient or you need more time. So since none of you guys are speaking, I assume 1 week is sufficient. Any comments, guys? You should be able to derive the equations from, and in fact, I will probably discuss also. Once you submit the assignments, I'll take that up in class also and probably solve it. But yeah, so this will be the first assignment. Okay, so now we are going to move on to the next important. So anything that we design or do, right? There's a figure of merit associated with it. FOM means figure of merit, meaning so when we say that okay, when we compare, let's say two designs or two materials, or it can be anything. When we are comparing, right? We compare so when we say that, let's say, I don't know any one of you, but let me take some random names. So Ayush. So let's say Ayush is better than Vaibhav. So no offense to Vaibhav, please. So when I say that, right, what do I mean? So let's say, what do I mean by better? Can I really say that Ayush is better? Better in what sense? Is Ayush taller? Is he more intelligent, or is he more hardworking? Or he's richer, or whatever, right? So there can be so many different parameters. So, and in the industry also, you will see it. If you join the hardware industry, you will see that figure of merit works like a summary. So when I say that Ayush is a better guy than Vaibhav, that means that there are certain parameters. So let's say, and it's not necessary that Ayush will be better than Vaibhav in all the parameters, right? So let's say Ayush let's say his CGP is higher than Vaibhav, but let's say Vaibhav is richer than Ayush, right? But then what we can do is we can associate weightage of each parameter when we are defining a person, or let's say when we are defining a design. So let's say when we are talking of an amplifier, when we say that amplifier X is better than amplifier, or better designed than amplifier Y, there are certain parameters we will say that okay, based on these parameters, so let's say we define the for the amplifier we define the figure of merit as, so let's say there will be two coefficients A and B. Now when figure of merit is typically higher, that means the numerator should be higher, right? So if we are talking of an amplifier, so when we talk, so let's say amplifier has different parameters associated with it, right? So one of them can be power. So which amplifier is better? The one which takes more power or which takes lesser power? We are going to talk about the other parameters also, but let's say, so we are trying to derive an equation, right? So which amplifier is better, guys? Some let's say the amplifiers are like doing the same performance, but one is taking more power and the other is taking lesser power. It's consuming lesser power. Which one will be better?
Lesser power.
Lesser power. So power will actually come in the denominator, right? Because lesser the power, the higher will be the figure of merit, right? Similarly, let's say gain, the DC gain of an amplifier, right? So I can say that DC gain higher, that is the better, right? So let's say the DC gain G will come here. And then somebody can say that, okay, one of my figure of merit for the amplifier is bandwidth, right? So bandwidth, 3 dB bandwidth, higher, the better it is, right? So I can say, okay, so bandwidth is B. So let's say when I'm defining a figure of merit, I can define the figure of merit in any way that is convenient. But typically there are standards which are followed. So for example, for an amplifier, I can say gain multiplied by bandwidth divided by power is my figure of merit. So you can see nobody cares about the dimensions as such, as long as we understand. So for example, when we talk of an ADC, I don't want to talk of an ADC here, but there also, the figure of merit is derived. I mean, when to, when engineers are talking to kind of summarize the whole characteristics of an ADC, we tend to come up with this concept of figure of merit, right? Which material is better or which design is better. So now we understand what is figure of merit, right? Have you been introduced? I mean, have you heard of this term figure of merit in any other course? Yes or no? Come on, guys, give me a yes or no answer. Have you heard about this figure of merit FOM terminology in any other course so far? I just want to know so that I'm aware that you have been introduced to figure of merit concept, or no? It's actually a real thing that you will stumble upon when you are discussing many other things when you actually start working. So because you guys are quiet, I'm assuming that you have not been introduced. Is it? So maybe Ayush, have you heard of this thing figure of merit? Ayush, are you there? Am I audible or not? Hello? Am I audible, guys? Just give me a yes or
Yes,
no answer.
yes, sir,
Okay.
yes, sir.
Okay. So have you heard this figure of merit? I mean, there's nothing
Uh,
wrong if you have not heard. I
no,
just want to.
sir, not for me. I have only heard it before.
Okay. So I'm assuming the figure of merit, the term figure of merit, has not been introduced to you in any other course, which is fine. That's not a problem. I just wanted to gauge. So when we are talking of figure of merit for a piezoelectric material, um, this concept of coupling factor comes into picture. So EMCC is electromagnetic coupling coefficient. E for electro, M for magnetic coupling coefficient, right? So electromechanical, sorry, not magnetic. I'm extremely sorry. Electromechanical, because it's a transducer we are talking about, right? We are talking of moving from electrical domain to mechanical domain and vice versa, right? So electromechanical coupling factor is a figure of merit for a material. So to say that, let's say, quartz is the coupling factor of quartz is better than the coupling factor of, let's say, PVDF, right? So that means quartz has a higher figure of merit, or it's a better material than PVDF, right? In general, that is in a nutshell. But that doesn't mean that we will not use PVDF anywhere and we will only use quartz, right? So um, so electromechanical coupling factor K is a figure of merit kind of it's a summary kind of a parameter wherein K square, it is actually defined by K square, and don't ask me why K square. I mean, I can answer. The fact is, somebody who came up with this term first, he put it K square, and there is no reason why it is K square. It can be K or it can be anything. But I think the reason why he put it K square, because probably he had in mind that we are talking about energy transmission coefficient, and also probably he wanted to show that or ensure that it's a positive quantity. It will never be negative. So K square is a figure of merit for a piezoelectric material, and it is defined as converted electrical energy divided by input mechanical energy. Please note, so this is not the same as efficiency eta or something. This is just a measure to show how much energy is converted from the mechanical domain to the electrical domain, or vice versa, how much energy is converted from the electrical domain to mechanical domain. So the first one will be true when we are talking of a actuator or a sensor. The first one we are going to refer as k square. So this equation will come into picture when we are talking of a sensor, right? Because in a sensor, the quantity that is given as an input is a mechanical quantity, right? And whatever is converted, the output quantity is electrical. So that is k square. Similarly, for an actuator, it is reverse, right? Converted, the input energy is electrical, whatever is converted is the mechanical energy. So the ratio of that is energy transmission coefficient, right? So let us derive this. So let us derive a mathematical equation for this figure of merit. So again, we have taken the same piezoelectric material, and we have a battery as we have shown. So by now we should be pretty familiar what is going to happen if we apply the battery in a direction which is opposite to the polarization direction, right? So the polarization vector arrow is shown here, and the battery, the electric field, is in reverse direction. So if we apply the battery like this, what is going to happen? The material is going to shrink from length L to L plus delta L, right? And delta L can be negative in this case, but the point is it is going to shrink, right? So that we have discussed why it is going to behave like that. I'm not going to talk about that again. And k square, right? Here, k square means energy that is converted divided by the input energy. So the energy that is converted is in which domain in this case? Or rather, let's talk about the energy that we are giving as an input. That is in electrical domain, right? So that is electrical energy, right? So the input energy that we are giving is given by half CV square, right? And C we know, we are defining C here as epsilon subscript T A by L, right? What is A in this case? A is the area of the surface A, right? This is the surface, right? A. And what is L? So this is the normal capacitor equation. Just that when we are talking of permittivity here, we are not writing epsilon, we are writing epsilon T, because this is under a given condition when stress is equals 0, right? And V we know is nothing but like what? Electrical field E is nothing but V by L, right? So V is nothing but E times L, right? So I'm just replacing all of this and writing it, in a simplified form, half multiplied by epsilon T A L E square, right? So now what is the output mechanical energy, or the converted mechanical energy I should say, is half. So from that spring equation we know half kx square, right? X is the deformation that it has undergone, right? So the converted mechanical energy is half k delta L square, right? So k, what is k? This is the spring constant k, right? And we had derived this value of k in an earlier form, right? You remember this in all of the earlier slides. We had mentioned k is nothing but a divided by L times the compliance coefficient. And here again we are talking of compliance coefficient with a constant, S as subscript E. Why we are talking of S subscript E? Because any charge that is going to develop, right, because of this deformation is going to be sucked away by the battery, meaning the electrical field is constant, right? That's the reason it's compliance coefficient at a constant electric field. So half kx square, x is the deformation. We remember that, right? we have a spring, and then if the spring deforms from x equal to 0 to whatever, x equal to capital X, then the energy that is stored is half kx square, right? That we have seen earlier, meaning from your basic 11-12 physics course, right? So the converted mechanical energy is this, right? So if I put this equation and this equation in k square, right, and try to um, so try to come up with this electromechanical conversion coefficient, right? So you see, so this guy mechanical energy is half. So delta L by L is nothing but strain S, right? And S, I'm further simplifying this. I have one more step to go. I'm further simplifying it. Delta L by L is nothing but strain, right? Delta L by L is strain. And we know strain for a piezoelectric material, S is equal to D times E, right? So S, I'm further simplifying it, and UCME becomes whatever I've shown here, right? So now I'm in a position to use this guy and this guy to come up with k square. And this is in absence of T. There is no, why am I talking of, epsilon T that is understood, right? There is no stress here, right? Because this material is free to move. I'm allowing it to move. So even though there is strain, there is no stress. So that's the reason it is permittivity at a constant strain, constant stress, and T is equal to 0 in this case, right? Because we are allowing the material to move freely. Now, if we see, we come up with a nice expression for k square, and this kind of makes sense also, right? Because higher the coupling, the piezoelectric coefficient, better will be the coupling, the electromechanical coupling coefficient, right? So this is one expression for k square. Any doubt in this? Anything that you didn't understand in this derivation? Everything was derived from first principles. If you see, everything was derived from first principles, right? The electrical energy is half CV squared, that all of us know. Only thing that is new in this equation is why, epsilon is epsilon T. That also we have understood why we are using epsilon T. V is equal to E times L, that we know from our physics, basic class 11-12 physics, right? This is again half kx squared. That is again known from class 11-12 physics, right? Only thing that I've done is this delta L, I've done some mathematical jugglery. So, so this is AL compliance SE. So what I did is I put L square, I divided this delta L by L, and some essentially it is the same thing. So, and with delta L by L, I can write delta L by L as my strain S, and S is nothing but it's proportional to the electrical field that we have applied, D times E. So this is one equation, and the first one we have already derived. So if we do this guy divided by this guy, we land up with this. Straightforward, right? This is actually pretty important. You will find k square in data sheets of piezoelectric material. This is clear, right, guys?
Yes, sir.
Okay. Anything? Yes, Nayan, you want to say something?
No, sir.
Clear, right? Okay. So this is one way of, as I said, so this is a figure of merit. So we should be able to figure out which one. When we are talking of electromechanical coupling coefficient, just by looking at k square, if we are comparing materials just by looking at k square, we should be able to tell that material X is better suited for overall. Material X, is it better? Does it exhibit better piezoelectric behavior than material Y or not? That we should be easily able to tell by just looking at k square. and this is what the equation for k square is, and you can derive it yourself. You don't have to mug up anything here. This is all basic equations, nothing to mug up. And then if you remember, the way we have defined the figure of merit is the converted energy, and it makes sense, right? When we are talking of a transducer, we are saying that it transducer converts one form of energy to another form, right? So we need to, how do we say that, this particular material is better than the other? The material which will do a better job in transforming the input energy to the output energy, whatever be it. Input energy can be electrical or it can be mechanical, but the material which will do a better job, that will be a, overall better kind of a, it will have a better figure of merit or k square in this. Okay. So I think we have only 50, it's already 12:54. So anyway, we'll then pick up tomorrow. Next we are going to talk about a simplified model and transfer characteristics, and then we are going to get into some amount of electronics, right? So it's already 12:55, and yeah, I think let's start with a simplified model tomorrow, and I will send you the assignments which you will have to submit. There will be weightage on assignment in the exam, and there will be a hard date also. And because all of you kept quiet, I assume that 1 week's time for the assignment is good. If you have a problem, please let me know now, because I'm going to send out the mail with all the details of the assignment. Any problem? 1 week should be good, right? Maybe up to next Friday. Okay, so because all of you guys are not, saying anything, I'm assuming that you are okay with 1 week's time. So I will post the assignment in Teams. You will have to submit. You know how to submit assignments, right? In Teams, that you know, right? You're aware of that, right?
Yes, sir.
Okay. Okay, great. So I'll post it and then we'll take it from there. So see you guys tomorrow then. We'll stop for the day. Bye.